Hello, everybody, and welcome to today's RustLab's conference. We are very happy you could join us. RustLab is a series of events dedicated to Rust, a young programming language which shows lots of potential. RustLab is organized by Develer, a company that develops hardware and software with industrial applications, with great focus on emerging and open source technologies. At Develer, we strongly believe in supporting training and collaboration. And because of this, we regularly organize technology events like conferences, workshops, courses, webinars dedicated to state-of-the-art technologies such as Rust. Before the beginning of today's talk, I just have a few announcements. If you experience problems with your connection, if the streaming stops for any reason, if you get booted out of the live room, you have to go back to the original email confirming the event and click on the link that you received in that email. You will be brought back into the live room and you will be able to enjoy the rest of the talk. At the end of the talk, we will have a Q&A session, and there will be a dedicated Q&A chat, different from the regular chat that you can use during the talk. So we would like to kindly ask you to wait with your questions and write them in the special chat that will be open at the end of the event, especially for this purpose. Finally, we would like to invite you to join our Discord channel to network and share ideas with like-minded people. You can click on the link above and you can join us there. Today's speaker is Gerhard de Clercq, who will talk about the challenges faced when trying to implement a proof-of-concept GUI in a system inspired by Qt 2 in Rust. So enjoy the talk and stay tuned for the Q&A session at the end.
Hi, I'm Gerhard de Clercq and I'm a software engineer at KDAP. Although I should mention I've actually only been a software engineer professionally from the beginning of this year. Last year I was still studying electronic engineering at university. So this talk's very much going to be the opinions of a 22-year-old who thinks he knows everything. Although it's actually not quite that bad. I have been doing semi-professional software development in my free time for many years now. And particularly, I've played a lot with C++, Qt, and a bit with 3D technologies, which is why I've ended up at KDAB, who, as you can see in the bottom right corner, are the Qt, OpenGL, and C++ experts. Although we do try to be experts in more than that, in software engineering in general, which is kind of why we're at a Rust talk. But yeah, so enough about me. The talk is entitled 2D Scene Graph GUI in Rust, which right now probably sounds like a bunch of gibberish, but throughout the talk we'll get to what all of those terms mean. Right now, 2D scene graph is really just a reference to Qt for anyone who's ever worked with that. So you'll see the subtitle is basically that this is a C++ engineer's journey on trying to replicate the basics of Qt in Rust. So yeah, basically it's just about how do we build a high-performance GPU-accelerated GUI stack in Rust. Although the Rust specifics are only really going to come in, the second half of the talk. The first half is more just about GUI stacks in general. Okay, so with the title out of the way, let's get to the background, motivation. Why am I giving this talk? What is the point? So to illustrate the point, I've come up with a hypothetical scenario. So let's say we've got a client who wants a high-performance GUI with smooth animations that works, but they also want this on a low-cost, low-powered embedded platform because, well, they want to make money, obviously. And traditionally, the only way you're really going to get high performance on a low-power system is by using a high-performance language like C or C++, because you do need to extract, the maximum performance you can out of the hardware to get that acceptable performance. Now, obviously, C and C++ aren't the only options around, but they are kind of the major options. You are probably using one of those two. And that's all fine and well, but C and C++ do come with a few, let's call them disadvantages or quirks or whatever you want to call them. And I think, the first major one is just safety. Okay, in these languages, you can do whatever you want, including, going outside the bounds of an array or freeing up memory twice, etc. And all of these things lead to, if you're lucky, just crashes. If you're unlucky, security holes. Um, a famous quote I've heard about C++ is that it gives you a lot of rope. In fact, it gives you enough rope to hang yourself, which I think is very true. And then the other not so nice thing about these languages is really in the form of convenience. If you've ever used a modern type language like Node.js, which has the npm package manager, you'll know how easy it is to install, libraries in those with these modern package managers. Now, there are third-party package managers for C++, but there was no official one. So you do still have compatibility issues, and a lot of stuff are just not package managed. So you need to install things yourself. The easiest way to really get a library in C++ is when it's a so-called header-only library, because then you only need to bring in one file. But that's sort of rare. Not all libraries can be made like that, and it's sort of debatable if it's such a good idea for compile times, etc., to even do that in the first place. And then the other thing is kind of also alongside package management build systems. There isn't a standard build system for C or C++. Right now, CMake has sort of become the de facto standard, but there's a lot of other stuff out there. Not everyone's using CMake, so it's not guaranteed to work nicely. Whereas, many modern languages do have their own build systems and everything just works with that. So then kind of, the whole point of this talk is that now we've got a new player in the high performance language space in the form of Rust, which is sometimes quoted with, the text fast, reliable, productive, pick three. So Rust tries to give you the same performance as you can get from C or C++, while also giving you safety and convenience, which is really, quite lucrative. And the way it achieves this is through this whole concept of ownership and the borrow checker. I'm not going to go into much of that right now. There are many resources online that you can go check these things out if you're interested. For now, I'm kind of going to assume that all of these things are true. And if we use Rust, then we can get systems which are fundamentally more stable, secure, and at least as fast as C or C++ systems. Although some people think that, Rust even gives you faster code or there's a thing that sometimes you can get faster. Your idiomatic Rust can be faster than your idiomatic C++. I haven't really, used it enough to say this is true, but it is apparently, it does apparently happen. And one of the things with Rust is it actually forces you to give the compiler more information about your memory. So in theory, the compiler can do more optimizations. But as far as I understand, none of this has actually been done in the compiler yet, so it's more of a future possibility. And now, obviously, I said Rust is a new option in the high performance space, which isn't quite true. I think it has been with us for over a decade, but it's more like the past year or two, I think it has really become a production grade option with companies like Microsoft, Amazon, and Google publicly stating that they are using this thing in production. So that's why I think, the rest of us can now also start looking at that. And this talk is about using it in the embedded GUI space, the high performance embedded GUI space. Although in my opinion, the high performance embedded GUI space is kind of like a worst case scenario for GUI. So if you've got something which works in this space, there isn't really a reason why it wouldn't work on something more powerful like the desktop. It's debatable, whether you're going to have the same API, etc. But performance-wise, I think if we can solve this problem, then we can have something which works nice on the desktop as well. So the idea is that in 5 or 10 years time, we want to have the full GUI stack in Rust so that we can get all of the benefits of that. It's very hypothetical. It's sort of debatable as to whether this is even a good idea. But for the rest of the talk, we'll assume that this is something that we want to do, and we're going to look at how should we approach it. Okay, so with that, with the goal laid out, and hopefully I've convinced you that we do want to rewrite the GUI stack in Rust. Otherwise, if you want more motivation on why Rust, you can go check out almost any other talk out there. Most of them start with half an hour introduction of why Rust. But yeah, we're assuming that we do want Rust. So now I want to talk about what is the current GUI situation in Rust. Is what I am proposing here not done already? And as far as I can tell, the short answer is really no. I've looked through all the existing stuff I could find, and there are plenty of attempts at getting GUI on Rust out there. A lot of them are quite exciting as well. And through my investigation, I've picked up that there are about two broad categories of libraries out there. The first category is basically Rust wrappers around existing libraries, and these existing libraries can be, things like Qt, GTK, HTML, whatever, like your operating system libraries or portable ones. Doesn't really matter. And under this category, you actually get two subcategories, to be honest. The first kind are really just thin wrappers around, let's say, Qt or GTK or whatever. So they try to give you the normal Qt API, just in a sort of more Rust style, or the normal GTK API in a more Rust style. And then the other subcategory are libraries like Moxie, which try to actually hide what the underlying library is. So they try to give you a very rusty API and then transparently map to some kind of backing library. And the idea is then that they can map to many different backing libraries to work on different platforms. Moxie's got kind of a React.js style API, but also tuned a bit to look right on Rust. Yeah, I'm not going to talk too much about those libraries because, as I said, the idea is to rewrite the full GUI stack in Rust. The idea of this talk isn't really about I just want my code in Rust and I want a GUI. So we're not going to go too much more into that. And then the second category of Rust GUI libraries are what I've called full Rust libraries. And the example I've given is Druid, but there are many other examples. So Druid basically does everything all the way from API to drawing. Although I should mention it doesn't. It's kind of debatable as to whether it does entirely everything, because Druid does have a dependency on a 2D rasterization, either library, library you can link in yourself, or an operating system API like Core Graphics on Mac OS. So currently Druid doesn't actually do the rasterization itself. As I said, on Mac OS, it uses Core Graphics. I think on Linux it uses Cairo. I think on Windows it uses Direct2D. But there's no real reason you could just replace that rasterization layer with one written in Rust. So I'll still give it to them that this is a full Rust library, specifically because they are at least doing everything else. They are doing layout, state management, rendering, all of those complicated stuff. Whereas something like Moxie technically only does state management in a way. I guess it does a bit more, but it really leans on the underlying libraries to do the heavy lifting. Whereas Druid does all the heavy lifting except rasterization at the moment. Okay, so then, yeah, as I've kind of mentioned, if you want a Rust GUI right now, if your only goal is to have your own code in Rust so that your own code is safe, and you want just a GUI, then right now you probably want to look at the first type of library. You want to look at something which just wraps Qt or GTK or whatever, so that you've got a stable foundation on which to build, and you're kind of going to get the same stability that doing Qt and C++ offers you, because, as I said, if you're using just a thin wrapper, there isn't that much which can go wrong in the wrapper. So yeah, you're definitely gonna want to look at one of those libraries if you're in the market to get a GUI right now. I wouldn't actually use Moxie, which I've listed here, as that is still very far from production ready. I'm not aware of any of these Rust libraries which try to be backend agnostic, which are production ready. So you're gonna have to go for one of those which are very much explicit about what backend they use, and they force you to be aware of that. But as I said, that's the only way right now with little effort that you can get a stable GUI. And then I think the full Rust libraries right now are very, very far from being production ready. So they are more relevant for the future, kind of the scenario that I've laid out for this talk, that in 5 or 10 years time, we want a full GUI stack in Rust for whatever reason. Maybe we want to build a new operating system in Rust, and we need a nice GUI stack. I don't know. But yeah, the second part is for the future, and that's kind of, this talk is about how do I think we should approach that problem. So yeah, just another comment. Druid, I've looked. There are others beyond Druid, but Druid looks sort of like the best one out there right now. The most well architected, most feature rich, and Druid is greatly inspired by Flutter, as far as I can tell. It uses the Flutter layout protocol, for instance. It's also got the tree diffing. So yeah, very very much inspired by Flutter. Okay, so now that I've hopefully convinced you that we do want to rewrite the GUI stack in Rust, there is this question about how low can we go? At what layer do we want to start just replacing stuff with Rust? And I think I've kind of alluded to this with Druid, where I said that the very lowest layer of Druid right now is actually outsourced. It's not in Rust, although you could definitely replace that with something in Rust. So let's first just talk about, what is the GUI stack? And I think we can all agree that the topmost layer in the GUI stack is really going to be the API that you give to developers. Any higher than that, and you're kind of in a specific application. So that's not in the GUI stack anymore. That's really a specific application. And then I think we can all agree that the physical pixels on the screen are the lowest level. That's kind of the goal. You write your code in the API, and what you're expecting back is pixels on the screen. You don't necessarily care about what's in between. But the question here is where do we start rewriting? Is lower necessarily better? Do we actually want to write everything from pixels to API purely in Rust? And I think the obvious answer sounds like yes, but unfortunately it's not quite as simple as that the moment you introduce a GPU into the system. And the reason for this is that a GPU, in simple terms, is really a hardware device that is designed to spit out pixels at an alarming rate. Okay, so and most modern computers and even embedded devices have very powerful GPUs. So if we want to have, the maximum performance GUI stack, we really do want to lean on the GPU. So we do need to incorporate that in the stack. And you don't really want to do anything that the GPU can do for you in your own Rust code. Now, I'm kind of here assuming that, Rust code here refers to code that we are writing and it's running on the CPU. I don't know if it's possible to write GPU code in Rust yet, but that's not really the. Let's not go there right now. Let's just assume that the GPU is part of your computer, and it's got an API provided by the operating system, and the only way to deal with it is through that API. So we're going to assume that that is something what we want to do. We don't want to try to do any rasterization in Rust, because the GPU can do that for us a lot better than any Rust code we can write will, under the assumption that Rust code is running on the CPU. Okay, so before I go into more detail on how we use GPU acceleration, let's first talk about how traditional GUI toolkits work. And by traditional GUI toolkits, I'm talking about something like Qt widgets, which has been with us for a very long time. It actually still works quite well for data-heavy large desktop applications, but it's not that great for embedded. You don't really want to use Qt widgets there. So many of these toolkits, they actually predate the GPU. It's not necessarily that they came before the invention of the GPU, but they were at least developed in a period where having a GPU in your computer wasn't mainstream. So these libraries are very CPU focused. They were designed to be able to work without a GPU, to be responsive and fast as CPU only workloads. And a key concept behind, as far as I know, basically all these libraries is that they are built on the concept of imperative drawing, where they send out commands like draw me a rectangle from point 00 to point 100, which which is sort of a natural way of thinking about things, sending out drawing commands, or some people in the Qt world you'd call these painting commands. It's a very intuitive way of describing what you want on the screen, and it's perfectly reasonable to implement this type of drawing on the CPU. I think especially, back in the day you only had um, single core CPUs were kind of the only thing you really had. A multi-core CPU was a special thing. So the CPU couldn't really do anything but draw one pixel at a time. So it was fine to give it these sort of commands. But then, with time, things evolved, and GPUs became a thing, and people became aware of the potential of GPUs. And so GPU acceleration was retrofitted into these traditional toolkits to speed them up. But it's not like the whole toolkits were reworked to be GPU based. It's more like they found specific places in these toolkits where you could add GPU acceleration to make things like scrolling faster. So it's not really built from the ground up to be GPU based, because the thing with a GPU is, as I said, it's this piece of hardware that spits out pixels. But the question is, what do you put into a GPU? And the answer is really triangles. There's a bit more to it, like you also give it shaders and whatnot. But what the point is, you give it in triangles, and it interpolates between the triangles and runs the shaders to decide which color each pixel should be. So there's this fundamental disconnect between your imperative drawing calls, right? The draw me a rectangle from what, coordinate this to coordinate that, and the triangles that you need to give the GPU. So if you want to do this kind of drawing on the GPU, then you need some kind of, magic inside your framework to transform all your imperative calls into something the GPU can understand. And, to be fair, many libraries have gotten very good at doing exactly this. I think one of the best out there currently is probably Skia. Skia is very good at this, but even if you are as good as Skia, there's kind of a limit to how good you can get. And what's also kind of problematic is the more magic you throw into getting this to work, the more confusing it becomes, the more there's a disconnect between what you're writing and what the system is doing, so you can't really reason about performance anymore. And at the bottom there, I've linked a blog post from a Mozilla graphics engineer about exactly this, how anything based on imperative drawing just isn't optimal for GPU, and we don't really want to go that way. So here's just an example of what I meant by imperative drawing. This is in Qt widgets, where I've got a Q painter, and as you can see, I'm telling it that I want it to draw a rectangle, and then I want it to draw text. And it's very, step by step by step, and then I get that. So now the question is, how do modern frameworks work, now that we've discussed the traditional frameworks? And surprisingly, many of them actually still use imperative drawing. Or at least, I think the biggest example that I'm looking at right now for modern toolkits is probably Flutter. Flutter is becoming very popular right now, and I think it's very modern because it has only recently started. I'm not actually aware of any other, major up-and-coming framework right now beyond Flutter, which is popular. There are many. There are a few .NET ones which are also, they are kind of inspired by Flutter, really, architecture-wise. But interestingly, Flutter still is based on Skia. And as I said, anything based on Skia only has GPU acceleration carefully added, inserted at points, and there's all sort of trickery to get that working. But these things are really optimized for GPU from the ground up. A major exception that I know to the only major exception I know to this trend is really Clercq 2, the topic of this talk basically. So Clercq 2 uses a completely different approach where it is optimized for the GPU from the ground up. It forces you to talk to the GPU directly, not to do any of these imperative drawing calls. And I think that is kind of the superior way to go about this. The only other thing I'm sort of famous thing I know which does this is WebRender, which the engineer I linked on the previous slide is working on. I'm not sure if they're still working on it, which is basically the experimental Mozilla browser, which is optimized from the ground up for GPU rendering. And as far as I can tell, it uses roughly the same concept as Clercq 2, although I haven't really been through the code. But yeah, so I do think this is the kind of superior approach for GPU-centric stuff. So now let's quickly look at, how exactly does Clercq 2 work? How does it achieve this GPU optimized rendering approach that I'm talking about? So here's a quick hello world example in Clercq, which looks exactly like the hello world I showed with QPainter. Okay, so technically I said it's in QML. If you've ever heard of QML or Clercq, you'd probably think these two things are synonyms. It's not entirely true. QML is technically the language that you see here on the left-hand side, and this JSON-like language which allows you to, in a declarative way, say how your GUI should look. So for instance, here you've got your rectangle and then you've got your text. And QML has got this concept of bindings. So here, for instance, you say that this thing should fill its entire parent, and you say this thing should be centered in its parent. And you can also do things like say that, the x coordinate of this thing should be the x coordinate of that plus 10, and then whenever the x coordinate of this thing changes, that one automatically gets reevaluated. I haven't put it here, but it's a pretty powerful concept. So this is QML, and then Clercq is actually the engine which is responsible for drawing this. It's sort of the behind the scenes thing. So yeah, I think right now there's not a big difference, but we will get into it. So the way that Clercq 2 works, the way that it achieves this GPU-centric approach, is through what they call the scene graph. Now I have to be clear that this term scene graph is really just I'm using it to refer to this concept because that's kind of in the Qt documentation what they used to refer to it. If you Google scene graph, you're probably gonna find something completely unrelated. As far as I can tell, it's not, it's not a fixed concept. It's sort of used all over the place and doesn't really imply GPU usage either. You could totally do this with imperative drawing as well, but for the context of this talk, let's just assume that scene graph implies you're using the GPU a lot. So the basic concept of the scene graph is that your GUI is composed of many different components, as I just showed with the rectangle and the text, or it could be higher level components like buttons. And then your components are composed of nodes. And nodes are basically things that can be drawn by the GPU. So I said there on the slides that nodes are backed by GPU primitives. Now, GPU primitives are basically my umbrella term for things that the GPU understands. So this includes, vertex buffers, index buffers, uniforms, attributes, and shaders. So when you define a node, and an example of a node is actually a rectangle, for instance. If you define a node, you need to define, okay, what triangles do I need to draw this node? What shaders am I going to run? What indices am I going to give it? What vertices am I going to give it? So the point is that the GPU can directly draw these nodes. There are no fancy tricks involved. No, you can just upload the node to the GPU and it's drawn. And the nice thing about this also is that the node understands how to update itself on the GPU. So if you, for instance, change the color of your rectangle from blue to red, The only thing that the node needs to do is it needs to upload the new uniform to the GPU. Everything else is already on the GPU. Whereas, let's quickly go back to my imperative case where I can show you that here it's kind of a problem. Okay, there's no, let's say you tried to GPU accelerate this concept and you tried to generate, triangles for your rectangle. There's no implicit state retention here. So there's no direct way to just update one uniform to change the color of the rectangle. You kind of need to rebuild all the triangles for these calls from scratch because, as I said, there's no retained state. Every time Qt widgets decide that it wants to redraw this thing, it just calls this function again, and it goes for all the imperative steps. Now, obviously, you can, bring in, as I said, some magic to try and keep track between different drawing calls and find efficient ways to optimize, the updates, but it becomes problematic, especially once your drawing calls become more complex than this. This is pretty easy to optimize, but when you start doing crazy stuff, it just kind of becomes impossible for the engine to keep up. Whereas in my scene graph case or the Qt scene graph case, all the nodes understand exactly what commands they need to send to the GPU to update from one property to another. So yeah, as I said, there are just no fancy tricks. Okay, so now let us quickly do a demo of Qt. Okay, so here's the Hello World application that I showed you, nothing special yet. But now let's quickly open this thing in Gamma Ray, a tool we develop here at KDAB, which is kind of like if you've ever worked on the web, you've got that inspect elements or developer console thing. This is kind of like that for Qt. Okay, so here is our Hello World thing with the rectangle and the text. Nothing interesting yet, but now we go over here to the scene graph tab, and then you'll see something interesting. Okay, so that's just the background geometry node, and the big rectangle. So if I open the material, you'll see here's the fragment shaders of that thing, and here's the vertex shader, and we can also look at the geometry. So there you'll see the two triangles which make up the rectangle. So yeah, this is exactly what I was talking about. This rectangle was defined in terms of triangles and shaders. Yeah, there's no magic behind that. And yeah, you'll see kind of when we look at the text, it is actually quite hard to do something complicated like text in this case, but we'll get into why that isn't such a big problem a bit later. Okay, so let's quickly talk about the advantages of the scene graph approach. The biggest advantage is that the GPU allows you to basically redraw everything for free. Because as I said, the GPU can generate pixels at an incredible rate. So asking it to redraw everything at 60 frames per second isn't really a problem. It can totally do that. Obviously within limits, like if your UI becomes too complicated, then it won't happen. But for now, let's just assume that it is powerful enough to redraw everything for free the whole time. And the advantage of this is that when you have a dynamic GUI, when you want to have stuff like animations, you can get them basically for free because your whole system is designed to redraw everything every frame. So animations aren't a problem. And kind of the reason this is an advantage is because the way that the traditional GUI frameworks achieved high performance without the GPU is actually by only drawing what they need to draw when they need to draw it. So they've got these complex mechanisms which keep track about which parts of the screen have become dirty. Like whenever you click on a button, it knows that it only needs to redraw that button, that small piece of the screen. So by only redrawing what needs to be redrawn, they can get high performance without a GPU. But the problem is when you start having a dynamic GUI where you've got all these things moving around on the screen the whole time, you basically need to redraw the whole frame, everything on the frame for every frame. And as I said, the traditional frameworks just aren't they weren't really designed to be powerful enough to do that. Okay, they only achieved performance by only drawing what needs to be redrawn. Whereas now with the scene growth approach, we've got something which actually, by design redraws everything. So it doesn't care if everything is moving around. It can totally cope with that. And the other advantage is really just greatly simplified architecture. You don't need this complex monster which translates between imperative drawing calls and GPU primitives. And something like Flutter can actually give you smooth animations, and the way they do that is by being very clever about where they inject GPU usage. Browsers as well, they put things on different layers, and then they actually use the GPU to move layers and whatever. So the magic really becomes complicated when they try to get these things working. Whereas in the scene graph approach, it's just implicitly there. A very simple engine just gives that to you. But of course, everything has its advantages and disadvantages. So I guess one of the biggest disadvantages with the scene growth approach is that nodes suddenly become very difficult to build, because it's kind of, as I said, because you now have to define your nodes in terms of GPU primitives, it becomes hard to make your own like rectangle node. In Qt for instance, this is also a problem. It is not common to define your own custom scene growth nodes in Qt. We at KDAP actually get a lot of work for people who want to outsource that type of thing to experts because they don't want to do that themselves. And the reason I'm pitching this isn't, just to get us more work in the future. It's just because I think it's fundamentally better. And to be honest, it's not really as big of a problem as it sounds. And the reason is because, as I spoke about earlier in Qt, you've got this composition, right? So if you do have enough basic or fundamental nodes in your toolkit, you never really need to define your own custom nodes. If you've got a rectangle and text, for instance, you can already compose those two things to get a button. You don't need to touch the GPU code. So in QML, for instance, that is typically how you build something. You just compose a bunch of basic nodes and create your own high-level component. You never have to worry about the GPU primitives. The only case where you really need to go into that is if you need something that, for some reason, you can't get through composition, or you've got a very complicated component and you need incredibly high performance. Then you can get some performance gains by writing the whole thing as a custom component so that it's just one node, because there's a slight overhead involved in managing individual nodes. So you can cut out that bit of overhead by merging them into one node manually, but it's still only going to be a minor benefit really. So it's not a common case to need to go there, and so I think it's a fair compromise. The other big disadvantage is kind of the same as the biggest advantage. And this is that everything needs to be redrawn constantly. And this is a problem when most of your GUI is actually static. So for instance, when you've got a large desktop GUI with a lot of data fields, where all those data fields don't change a lot, then this becomes a problem because then performance doesn't scale with data anymore. The more data you throw at it, the GPU needs to go through all of that data for every frame, so it's going to start slowing down. The point at which this happens obviously depends at how powerful your GPU is, but fundamentally this is just a bad idea if you've got a complex, mostly static GUI. The traditional approach doesn't actually care if you throw more data at it. It only cares about how fast is the data changing. But I don't think this is such a major problem either. There are many optimizations you can layer on top of the simple scene growth approach to actually get it to deal with stuff like that. An example optimization is, let's say you've got this big complicated GUI, of which a large part is mostly static. So, let's say you've got your tree going like this, and then you've got a whole subtree right here, which is mostly static. So a simple thing you can do is to just take that whole subtree and render it into a texture, which is essentially an image. You just squash it into an image, and then you only put that image, that texture, in the root tree. So whenever the root tree needs to redraw, this whole subtree just becomes the operation of drawing an image, which is that's pretty fast, so it's not a problem. And then whenever, when the rare event comes along that something deep inside that subtree changed, you just re-render that subtree, put it into the image, and draw the image again. But yeah, and there are other optimizations you can do, like you need recycler lists or virtualized lists for having long scrolling lists. Because let's say you have 10,000 items in your list, you can't like have a scene graph node for all 10,000 items, especially when only 10 are going to be visible. So you do need to start, adding stuff on top of here to optimize for those cases. But I don't think these optimizations are nearly as complex as the optimizations you have on getting the traditional frameworks working on GPU. And it's still very easy to reason about these types of optimizations and the performance implications of them. So yeah, I think this isn't actually a problem. Just be aware that if you do a trivial implementation of the scene graph, it isn't going to cope with a lot of data. It's just going to fall over. Yeah, and then the other big problem with this approach is that you kind of need a GPU, right? The whole approach is based on the concept that we have a GPU. It can redraw things quickly for us. Yeah, so you do kind of need that. But I think that in 5 or 10 years' time, basically everything's going to have a GPU. Okay, today that is almost true. It's not 100% true. You do get, especially very low cost embedded platforms don't have GPUs, and we do deal with that at KDub. But I think, in a decade or so, that just isn't going to be true. So let's just optimize for the case where everything has a GPU. I think we've reached that point. Um, yeah, and you could totally have a CPU fallback. I've recently come across this thing called Swift Shader, which is basically a CPU renderer for Vulkan. So you could have, if you're building, let's say, an operating system with this approach that I've mentioned, the scene graph approach, and you do want the operating system to still be able to show something if the GPU isn't available, the driver's crashed or whatever. You could totally have a software fallback, but you don't want to do this. This doesn't. You don't want to do this for high performance stuff. It can only be a fallback because if you're doing software rendering on the CPU under the assumption that you've got a GPU, things are just going to go wrong. Okay, like you'd be better off with the old toolkits in the case where you actually don't have a GPU. Okay, so now I want to quickly talk about WebGPU, and I'll discover why I want to talk about that in the next slide. So first, let's just discuss the problem that I think WebGPU solves, right? So in this whole scene graph approach that I've just discussed, I said that we need to write nodes directly against the GPU. We need to give it GPU primitives, use the GPU API. And the question now becomes, what API do we use, right? Because there is no such thing as the GPU API in 2020. You've now got different APIs on all the platforms. You've got Vulkan, Metal, DirectX 12, maybe even something else is going to come along at some point. So back in the day when they created Qt 2, this wasn't the case. They used OpenGL because OpenGL, or more specifically OpenGL ES 2.0, could run on basically anything with a GPU. But that really isn't true anymore. OpenGL is dying quite fast right now. For instance, it's been deprecated on all Apple platforms, and it doesn't quite give you optimal performance. There's a bit of a disconnect between the abstractions that OpenGL gives you and how GPUs really work. So it's really fallen out of favor, and you don't want to build something new on OpenGL. Now, Qt has actually recognized this. So in Qt 6, for instance, Qt Quick isn't built on OpenGL anymore. Qt have created their own thing called RHI, which is basically, a translator from its own API into Vulkan, Metal, or DirectX, or even OpenGL. So even they have actually moved on. But RHI is very much a Qt only thing. It's not a public thing you can use, and it's very much optimized for their use case. So yeah, we're not gonna look further at RHI. And then yeah, so as I said at the bottom, the question is what do we do? Are we going to need to write our nodes in all three of these frameworks all the time? That sounds quite shocking. And I think the answer is actually no. Luckily, there's been another new, recent development by the name of WebGPU, which, as far as I can tell, and in my opinion, is kind of like Vulkan for the web. So it's similar to we had WebGL, which was basically OpenGL for the web, but this now tries to be in the style of the more high performance libraries for the web. But the interesting thing is that it's not only for the web. You could use it for any application really. Um, so what the way WebGPU currently works is they've got two reference implementations for it. One is written in Rust, coincidentally, the one by Mozilla, and then there's also a C++ one from Google. So WebGPU is really just a spec, and then the two reference implementations take this specified API and they translate that into Vulkan, Metal, or DirectX 12. And they've even got sort of, best effort approach for OpenGL. But, basically they have a common high level API and they translate that to the best API for your platform. So it's kind of like the RHI that Qt is using right now, but it's going to be a standard that's actually even going to work inside the web browser. So if we build something on top of WebGPU, we're going to have something which uses the right rendering framework on all the platform and even works on the web. So I think this is quite an interesting opportunity. And in many ways, they say that WebGPU tries to be the new OpenGL. So it is a bit simpler to work with than, say, Vulkan, which is sort of true of OpenGL as well. So yeah, I think WebGPU is a really natural fit to solve this problem we had, because if we write all our nodes in WebGPU, we only need to write them once, and they are going to work everywhere. And we are quite lucky that Mozilla has a WebGPU engine in Rust for us, so we can totally put this inside our Rust only stack that we're going for. But just a quick warning. The WebGPU spec hasn't stabilized yet. It's constantly evolving. So don't go out writing all your nodes in WebGPU just yet, because they are definitely going to break. Like for instance, they have actually updated WebGPU since I've started on my toy implementation of this concept. So my thing is already broken. If I just update to the new version of WebGPU, maybe at some point I will do that, but maybe I'll just wait until the stable release before I bother. So yeah, just a warning right there. But I think we can totally start working on the rest of the getting all the pipelines ready and stuff, but leave the bulk work of pumping out nodes for a bit later. Okay, so right now I want to talk about SceneGraph RS, which is basically my toy implementation of this SceneGraph concept we've been talking about in Rust. So now it's going to get a bit more technical and a bit more Rust specific. Okay, so now I want to lay out the goals for what I try to achieve with SceneGraph RS. So obviously from the title of the talk, you'd remember that I want to implement a 2D GPU scene graph in Rust, but that wasn't really my only goal. I've only started learning Rust or reading the Rust book about 4 months ago. So the project was really also an excuse to get to know Rust, um, and also an excuse to get to know WebGPU. I haven't used that before either. And then I also wanted to learn some lessons. So this current incarnation of SceneGraph RS isn't really a serious attempt of building the system I envisioned. It was really just an attempt of going through it quickly, getting to learning lessons, getting to know how to actually do it properly. And as I said, this is the first time I'm trying to build something in Rust. So obviously, I did everything Rust specific very wrong as well. Okay, so the main concepts in the system, how does it work? Coming back to how I said Qt Quick works, the core concept of the scene graph is that at the lowest level, it needs to have nodes that understand how to draw themselves. So these are nodes which basically talk WebGPU. And then the idea is you are able to compose these nodes into a graph in order to build up a complete GUI. And each node can have children. And the implication of that is that by having children, you are able to compose individual nodes into components. Because let's say you've got your parent node in a button, and it's got subnodes which are like text or maybe the board or whatever. Then what you want is that whenever you apply a transform to the parent node, you and a transform here is something like translation or scaling or opacity or whatever, you want that to automatically be applied to its child nodes as well, so that it looks like they are one thing. That's very important for composition. So as I've stated here, each node in my system has its own transform matrix. And the transform matrix is basically, what you use to position an element. But the transform matrix of a node is only relevant to the coordinate space of the parent. So if you've got, a text node, which is a child of a parent node, and you say that it is at, x10, y10, then that is relative to the origin of the parent. So the implication of this is that, the effective transform applied to every node is this local transform matrix of each node multiplied by the parent transform. So, this step here is basically how the whole transform propagates from the top of the tree down to the, lowest node you have, and that's how things move together, and you've got this composition thing. And basically, the seed graph engine is responsible for propagating all these transformation matrix updates to children. So it's the seed graph's responsibility that whenever you change, let's say, the x-coordinate of a node, that all its children's transform matrices should be updated as well to keep the coherence in the what is displayed. Okay, so now that I've given you a quick overview of how it looks or how I'm going to do this, now I'm going to give you a demo. Okay, so here's just the project source code open, and now let's run it. Yeah, so right now this is a really basic implementation of my concept. It has only got these button-like elements, and it understands about user input, bounding. So if I click on a random place, it does nothing, and if I click on this one, then it moves left, and if I click on that one, then it moves right. And this background is just an image node. So the way I built the button is through composition of just a rectangle node and a text node. Although I should mention my text nodes aren't quite like the cute quick text node I showed you earlier. I don't have that level of complexity yet. These text nodes right now are only image nodes. So the only thing I do is I wrap an image node in something which, when you set the text property, it uses CPU rendering to render the text into an image, and then it just uploads that image to the image node. So I don't quite have high performance text yet. But then again, doing text through this image style thing isn't that bad, because text doesn't, well, I think a lot of text doesn't change quite often, but for text which does, maybe not the best idea. But I mean, it's getting high performance text in the scene graph is actually quite a complex thing. There's a trade-off between putting it in a texture and actually using the GPU to rasterize text, because text actually has very complicated geometry, right? You've got, like, if you have to triangulate every letter, that actually becomes quite complicated. So yeah, I'm not going to get into that, but there's a lot you can do around optimizing text. Yeah. So now let's quickly have a look at how I implemented this. So this is basically the main file for my demo application. The first part of it is really just boilerplate. So yeah, I'm setting up the event loop, and then I'm setting up the scene graph with the event loop. Then I have to do this ugly thing where I wrap wrap the scene inside an RC and a ref cell, which is kind of something you need to do in Rust at times, because the thing is that I need to pass the scene into the event loop. I need to move it in there. Yet I also need to use it when I need to reference the scene when I'm constructing nodes on it. So the only way I can really get it to still be at the same point in memory before and after the move is by wrapping it into this RC, which is kind of similar to a C++ shared pointer. And then refcell just allows that thing to be mutable, because by default the contents of an RC isn't mutable. And then caller map we'll get back to soon. So yeah, here I'm just creating my background node, and I'm creating it inside the scene. And then here I'm creating my first button, the go right button, giving it a color. And then I'm creating the second button, the go left color, the go left button, giving it a different color. And then here you'll see I'm setting the X and Y coordinate of that button. So the first button and actually the background by default, they were at coordinate 0, 0. Now the second button is slightly offset. And then what I'm doing is I'm registering event callbacks on these buttons. So specifically, these are for the click events. So you'll see that for the first button, on the click event, what it does is it moves button 2 10 pixels to the right, whereas on the second button, what it does is it moves it also button 2 10 pixels to the left. Now, what's happening right here, I'm not actually cloning the button, right? So this is kind of something that I was also forced into doing by Rust. Yeah, it's kind of difficult to explain, but the idea is that I want to keep a reference to this button inside this this callback function, which is just a heap allocated closure, and which basically means that the only way you can have something inside the closure is you can either use a reference or you can move it into the closure. But in order to use a reference on a closure that you just store somewhere, for instance, I want to store this inside the button so that I can run it every time the button is clicked. Then it kind of needs to be a reference of a static lifetime, which is a bit of it's a very hard constraint to put on something, and it's not a constraint that I want to put on stuff. So what I've instead come up with is that these things are actually just handles. They are not, they don't actually contain the button state. They internally have this basically. So internally they point to the data of the button, which basically means that whenever you clone this thing, which is just a handle, the clone still points to the same button internally. So what I can do is, now that I have a cloned handle, I can move the clone handle inside the closure. And now I've got something which points to the correct button, and I can store it inside the closure without the requirement that it needs to have a static lifetime. And because this internally uses RC, the reference counting system ensures that the internally referenced button will actually stay alive as long as this closure stays alive, so there's no memory leak or reference issues here. But yeah, unfortunately, the Rust syntax for doing this kind of thing is a bit awkward. Like in C++, you can implicitly say that you want something to be cloned when you put it inside a lambda, whereas in Rust you can either say that everything should be by reference or everything should be moved. So unfortunately, when you want something to be cloned inside the closure, you need to create a clone yourself before moving that. That's a bit unfortunate. I hope at some point they change it. But yeah, yeah, it's not that bad. And if we are building, the real version of this system, we could probably hide this type of ugliness behind some kind of macro. So long term, this isn't the end of the world either. And then an interesting thing I want to also talk about is that I said that I wanted to move these closures inside the buttons so that it's stored, stored inside the button so that when it's clicked, it knows what to call. But that actually didn't work out. I'll go into why that didn't work out right now. So what actually happens is that the callbacks are actually stored inside this thing called the caller map, and not inside the button. So as you'll see here, when I create a new component, I need to actually give it a reference to the caller map. So what happens is that every component knows about every event that it can generate internally, and it basically registers that event with the caller map. It gets a unique ID for the event, and then it registers. And then what happens here is that this closure is put inside the caller map on the list associated with the ID for the clicked event for this button. And then what happens is every time the event loop is run, and the event is passed to the scene graph, and the scene graph gives the event to every node inside the scene graph. And then a node can basically look at the event and decide which of its internal events need to be handled. So it gives you back a list of IDs. And then once the scene graph has walked the entire tree and got all the IDs, then it goes through the caller map and executes all the call maps for the IDs which were returned. Okay, so now I think this sounds really weird, and it is a bit weird to me as well. Originally, I tried keeping a list of callbacks inside every node so that I could just immediately, in the function which processes the event, just immediately call the callback. And I actually, I wrote all the code for that, and it was going fine until I finished, at which point I couldn't get my code to compile. So the borrow checker was really mad at me about that concept I had of storing events directly inside the nodes. And at first I didn't really understand why it was so mad at me, because in a language like C++, doing that is perfectly fine and it would work perfectly fine. So yeah, this frustrated me a lot, and I tried all sorts of tricks to get it working, and eventually I gave up. But I also realized that the borrow checker was actually trying to tell me something important. It was trying to tell me that what I'm trying to do here is actually a very, very bad idea, because if you do things like that, you can actually have a situation like, let's say you have two nodes on top of each other, and let's say for some reason your event handling logic specifies that both nodes should process that event. I'm not entirely sure why that would happen, but let's say both need to process that event. Okay, so now you're walking the tree and you're giving this event to the top node, right? And there's a callback registered on the top node, which causes the bottom one to move in response to a click. So now, you run that callback and the bottom one is moved. Now, all of a sudden, when you continue walking the tree and you're now at the bottom node, its position it isn't actually under the mouse click anymore. So it doesn't receive that event anymore, even though when the user clicked, the button was clearly, or the node was clearly behind the mouse click. So now you've actually got this error where it doesn't receive the event because the first callback caused it to move. So yeah, that was actually a clear, bug or design flaw in my approach, which Rust didn't allow me to do, which I actually found quite pleasing in a way. This sort of reinforced the safety that Rust brings, in my mind at least. So what Rust forced me to do is to separate, the part where I walk the tree and the part where I actually execute event handlers, which I think is quite neat. It introduces this, very strange principle, but it forced me to do something which is fundamentally a lot safer. So I found that quite interesting. So now let's quickly just look at how these button nodes are created. I won't go into too much detail because there's quite a lot, but just a basic look at it. Okay, so the first part is just, here's the button state that's in a struct. And the state also needs to be, it's also implicitly shared, as I talked about earlier. And because you want to be able to just copy the handles to put them inside a closure. So you'll see that, yeah, I've got a comment here that the state actually needs to be shared. So state is separate from the actual button struct. We'll see here that the state has got a reference, that the button has got a reference to the state. And then the button also has an image node and a rectangle node. And these node classes are also actually implicitly shared in the style. But the implicitly shared data here isn't state. It's sort of, as I call, the GPU primitives, really. It's the internal image struct, the internal button struct. So basically, when the button is constructed, as I said, it renders the text to a texture, and then it gets the dimensions, etc. Then it creates a rectangle node of the same size as the image. Then it creates an image node with that texture. Then it sets the image node to be a child of the rectangle node, so that they now become one element in the tree, sort of, or not, they're not one element, but when you do anything to the parent, it is automatically applied to the child as well, so that on a high level they appear to be one component, which is what you want. Yeah, then it just basically populates the struct, and here it does that. It talks to the caller map and registers the on-pressed event for the rectangle node to set up the click handling, as I discussed. Yeah, I also just added my own. So apart from just registering the callback for external events, I also set up the logic for just making the rectangle color darker whenever the button is pressed, and then just resetting it when it's released. Yeah, and then these are kind of just boilerplate, because they are, yeah, I'm forwarding the click event. When it's registered on the button, it's actually registered for the internal event of the rectangle. So these are the pressed events of the rectangle. Yeah, there's not much interesting here. Okay, so now let's look at the rectangle node. The structure I came up with for how things looks is actually quite complex, and I do want to redo this eventually now that I understand a lot more about Rust, etc. I tried doing things in a C++ way initially, and then I was sort of forced into doing things in a more Rust way along the way. So the architecture evolved a lot over time, and it doesn't necessarily feel that natural anymore. But this is what we have. So for each node that I have, I've basically got a module, and then this is the root module. The root one is only it's basically just responsible for actually constructing it, and then it's got these high-level functions where you can, for instance, set the color or register callbacks. And here you'll see that internal sharing that I talked about on nodes. As I said, these things are also these nodes are also just handles. You'll see this thing actually. It's a node handle. It's a type defined. Yeah. So whenever you want to set the color of a node, what I actually do is, each node also needs to keep a reference to the scene graph, so that it can. Well, so basically, what happens here, and we'll get into why it uses the ID a bit later. I've got a slide about that. So what it does is, whenever you need to set the color of the node, you go to the scene graph and you get a reference to the node, and this is basically just the instruction queue for WebGPU. And then you ask the node to update its color using the instruction queue. So all it's doing right here is it's basically issuing the instructions that need to be given to the GPU in order to update the uniforms of the color. And then all I'm doing is, after the color has been changed, I just tell the scene graph that we need to do a redraw. This doesn't actually force a redraw immediately. the scene graph only redraws when it gets a redraw event on the event loop. So the first time you call this, it sets a dirty flag on the scene, and it issues a redraw event. It puts it on the loop queue, and then that dirty flag is only reset when the redraw actually happens. So if you're calling a lot of these things, they are all going to see that the dirty flag was already set. So they're not going to issue another event on the queue. And then, only when you return to the event loop is it going to dispatch that redraw event, and it's actually going to redraw the scene. So currently, I'm not redrawing the scene if nothing has happened. One of these things need to be called for some reason, and then the entire scene is redrawn. So, as I said, it's kind of I ended up with a rather complicated approach, but basically all the nodes right now are composed of two different internal elements. One is a basic node. So this struct basically just contains all the properties that all nodes in the scene need to have, which is basically that they have a width and a height, and an x and a y, and the logic which acts on that state, the whole propagation of the transform between nodes is all applied through the basic node part. So the scene graph understands how to interact with the basic node, and then your node specific behavior, which the scene graph doesn't actually understand, that you just put in the node substruct. So here, the only property on that is basically the color. So that's the rectangle color, and then here, as I said, is the width and the height. And so here's the logic for the specific node. As you'll see, the way I've structured it is that a node is actually composed of other internal structures as well. So the one part of the node is the pipeline, the other one is the internals, and then the other one is the signals. Now, signals are basically just, as I mentioned earlier, the possible events that can come from this node, the things that are registered in the caller map. Yeah, that's not particularly so. Yeah, I just store a vector of IDs inside the caller map, which need to be returned. So you'll see that. Okay, and then another interesting concept that I was sort of forced into by Rust is that I had to have a distinction between a node and a attached node. So basically, when you create the initial node structure, that is kind of just a request for node. So that says what the width and the height and the color should be, but it doesn't exist on the GPU yet. So you don't actually have any GPU primitives associated with it yet. And what then happens is at some point you attach this node to the GPU. So you give it a reference to the scene graph, and then it goes and it takes all the properties of the node and generates the corresponding GPU primitives. So what actually happens is that the original request is basically consumed, and it returns you an attach node, which does have the associated GPU primitives. And I've kind of split that up into, I call it has a structure which manages the GPU primitives, and that is basically called the internals. So, and internals are generated the moment that you attach the node to the scene. And then you end up with an attached node which contains all of these things. So it contains the internals and the basic node and the node itself and the signals, etc. So this is also just a handle, as you'll see. Well, actually, no. This is the high level thing is a handle for this. So what I actually had to do is that all the separate parts of the attached node are ref cells, so that you can mutate the separate parts of it individually by just having a non-mutable reference. And there are reasons for this, but it's kind of complicated. I also don't think it's really the best way. That was I was talking about where the architecture I came up with is a bit awkward. I think, when I redo this, eventually this whole having everything a separate element, that's probably going to go away. But yeah, anyway, so here's the process event function. So as you'll see here, it just uses a match on the event which comes from the scene graph, which is either left press or left release or keep press, and then it just, as I said, you keep this vector of IDs and you pass that once an event is processed, and then after all the nodes are walked, you can process those event IDs. So yeah, just coming back to everything stored inside the nodes. As I said, the internals are kind of the GPU primitives you have, like the index buffer, vertex buffer, etc. And then the pipeline is a WebGPU pipeline. So the pipeline basically describes to WebGPU how this node is rendered. It lays out all the GPU primitives required to render the node. So here you'll see here's a uniform layout. So this describes to the pipeline, how do the uniforms look for this button. Yeah, and then, there's a lot of properties I won't go into. These are mainly just defaults that I got. Most of them don't have anything fancy. So then here I'm loading the vertex shader, there I'm loading the fragment shader, and then here I'm setting up the pipeline. And yeah, so you'll see here's the final pipeline where it's got a vertex stage, fragment stage, rasterization stage, and there I describe where the vertex buffers are. It looks bad, but it's really not that bad. So an interesting optimization that I already have in my implementation is that pipelines can be reused because these pipelines are sort of generic. Like if you've got two different type of nodes which actually use the same, which have got the same uniforms, the same, yeah, like the same pipeline basically, then the scene graph reuses the pipeline. So what the scene graph does is every time you call render on the scene graph, it walks the list of nodes, and it attaches the so the way that you need to do rendering in WebGPU is you first need to attach a pipeline. Yeah, so let's just quickly go to the okay. So here's the render function for the rectangle node. So as I was saying, the way that WebGPU works is first what you need to do is you need to attach a specific pipeline so that WebGPU knows how to render what's coming. And then what you need to do is you need to bind your individual buffers. So yeah, I'm binding the uniforms, and then I'm binding the vertex buffer, then I'm binding the index buffer, and then finally I'm telling it to draw. So what happens is that you've got actually, changing the pipeline does come with a bit of overhead, and it's expensive. So what you do want to do is you want to take all your rectangle nodes, attach the pipeline once, and then call render on all of them, and then move on to a different type of node. So the optimization here is that the scene graph is actually responsible for attaching a pipeline, and that's part of why I ended up having pipeline as an associated type on the node. So what the scene graph engine can then do is it can query a node to ask what is the ID of the pipeline that you use, and then the scene graph maintains a map, a hash map of these pipelines. So whenever you register a new node on the scene graph, it checks if it already has a pipeline for that node. If it doesn't, it just builds one, or it constructs one, allocates one, whatever, and stores it in the map. So then whenever it goes through the render call, it only has one instance of every unique pipeline in the system, and it reuses the pipeline. I haven't optimized it that much. I haven't actually optimized it for reuse yet, but I do at least have it set up so that it has the map, etc. But there's not really intelligence behind grouping different nodes with the same pipeline yet. Um, so yeah, just looking a bit more at the node internals. Here you'll see I've got a function which actually calculates, the triangle vertices for a rectangle. Not very complicated. And then here's the uniform for the rectangle. So the first one is the scene graph transform. As I talked about, this is actually responsible for positioning the node. In my implementation at the moment, that is all it does. In Clercq, for instance, this does a bit more than just positioning it. It does scaling and rotation stuff as well. Mine can totally be extended to do that, but at the moment, it's only the only things in here are X and Y. And then the other uniform is the color for the rectangle. So as you'll see here, now I've got some functions for just updating these uniforms in response to either having an updated transform or having a new color. And then you'll see all the individual things which make up the internals for the specific node. And then when the internals are allocated, you'll see I'm actually creating the vertex buffer, I'm creating the index buffer, I'm creating the uniforms, etc. And you're coming back to what I said much earlier in the talk. This is only done once, right? When the node is constructed on the scene graph, it generates all these things, and then they just stay there. They are not reallocated every time you do a draw call. They just stay here, and whenever you need to change the color, the only thing you do is you update the color uniform. And yeah, well, actually, you're calling this function, which is updating the uniform, and then just telling the instruction queue to write this new uniform into GPU memory, and then next time draw is called, the GPU will draw it correctly. Yeah, so I mean, there's a lot of code here, but it's not really that complicated to understand. And I've tried refactoring a lot so that all the shared code between different nodes are stored in, like this node, this generic node class here. So code for, like for instance, making new internals or getting the transform, etc. They are all stored. You don't have to copy and paste that, which is one of the things you do want in Rust, is to really use macros and traits and whatnot to never repeat yourself. I don't think I've gotten that right, but I do have it a bit right at least. Yeah. So yeah, let's just also look at, for instance, the okay. Let's first just look at the vertex shader for the rectangle. So this, if you recall the fragment shader, vertex shader I showed you earlier for the Clercq rectangle, this actually looks quite similar. As you'll see, the position here is just the final position is basically just the scene graph transform multiplied with the vertex position. So when I created the triangles in here, the coordinates I use are basically in the coordinate space of this node. It's not in the global WebGPU coordinate system. It's just in the coordinate system of the node, which is why, and this is achieved basically through the scene graph transform matrix. And that ensures that whatever you have here ends up being in local node coordinate space. And then the fragment shader is also super simple, really. It just takes that color uniform that you pass in, and it sets that as the fragment color, and that's it. So you can obviously do a lot more interesting stuff here. I haven't yet, but yeah, the possibilities are endless. Yeah, there's a lot more code in here. I really don't have time to go through all of it. I'll just quickly scan through the scene graph as well. You see when you want to create a node, you need to insert it into the scene graph, and then it registers it everywhere. And there's, some to set the parent of a node, you also need to go through the scene graph so that it keeps consistency of everything. Yeah, and here, for instance, whenever you change the x or y of a specific node, this function is responsible for propagating the effects to all the children of that node. Yeah, it's not a lot more to that. We've also got the WebGPU renderer, which yeah, so here's kind of the thing that I was talking about, where it gets the pipeline for an individual node. So it starts by setting the pipeline for the first node, and then it just loops for all the nodes and updates the pipeline, and then calls node.render. And there's a lot of optimizations we can still do in here. But yeah, I think hopefully I've illustrated it good enough for now. Okay, so now I quickly want to talk about the main challenges I faced when I implemented this thing in Rust. The first 3 points are kind of a bit of a joke, right? So the first thing that I really struggled with is understanding the borrow checker. As I alluded to earlier, I fought with it a lot. Yeah, if you want to go into Rust, this is something you do need to understand. Interestingly, I didn't find it hard to understand the goal of a borrow checker and what it does. What I found more confusing is just the actual syntax of the thing, learning how to tell the borrow checker what I'm thinking. It's not the most straightforward thing to annotate, really. These lifetime annotations take a bit of effort to master. I haven't mastered them yet. For instance, it took me a long time to realize that you can have an individual function, lifetime annotation for an individual function. It doesn't have to be for the whole implementation block. That changed a lot for me. But yeah, it's a bit unfortunate that actually writing these lifetime annotations is so hard, even if you understand what you want to tell the borrow checker. But I don't think they can make the syntax better. I think it is as good as it's going to get. So you just have to learn that. It's a bit unfortunate, but yeah. And then, after I understood what the borrow checker does, why it's there, how it works, I struggled with bargaining with it. So yeah, it's kind of as I said with those event handlers. Like I knew why it was mad, but I didn't really know how to fix my problem. So I tried all these weird tricks and begged the borrow checker to let me do what I want. But it wouldn't budge. So then the third thing I had to do was to just let the borrow checker win, take a step back, break up my code into separate sections. Basically just let the borrow checker win. Realize that there's a reason why it's complaining. My architecture is probably just wrong, and yeah, I needed to rework things. So I think that's a key thing when you're trying to do something in Rust, is whenever it feels like you're fighting with the borrow checker, you're really struggling to get something working, then it probably means your whole approach is just wrong. So you need to take a step back, or maybe many steps back, and just reevaluate how you're trying to approach the problem. So yeah, that's basically the fourth point that I've got here. If you're fighting a lot of a project, it's probably not that you don't understand the language. It might be that your annotations are just wrong. But if you're really deep into this and you're sure that your annotations are right and it's still complaining, then there's probably some deeper problem that you're not seeing, which it's actually trying to warn you about. So the solution, as I said, is to try and de-object orientate your design, right? Rust really hates it when you have references to things all over the place. It's if you've ever dealt with Rust, the core principle of a borrow check is that you're not allowed to have a reference to something whenever you also have a mutable reference to it, because that can introduce race conditions. Or in a multi-threaded case, in a single-threaded case, it's sort of debatable as to the benefits of that. But the main thing is that in the multi-threaded case, it introduces race conditions, so it's just not allowed, which is why keeping references around is a is a bad idea and something which makes a borrow checker very angry. So you need to do that thing that I did with a caller map where you don't try to store everything inside the object, okay? You store it somewhere else so that you can't access it at the same time and not introduce race conditions. So de-object, I don't know if de-object orienting the design is fully the right word. It's more about just not trying to store everything, specifically references, inside your objects. And then the other challenge that I had when doing this implementation is in terms of handling GUI state and deciding on what type of API I want for this thing that I'm building. And I don't have an answer to this yet. It's really open for discussion. Right now, I have this very imperative, as I showed you, this very imperative API where you need to say, button.setXY every time there's no state variable which you can just update and have things happen like you have in QML or in Flutter or in React.js, whatever. So yeah, I haven't figured this out yet. That's what a lot of the other Rust libraries are still trying to figure out as well. Um, we need to figure out something which is convenient to use, which creates very understandable code and works with Rust. Yeah, so that is a thing to still look at. And then I quickly want to go through some tricks that I learned while doing this implementation. A lot of these things are quite likely anti-patterns. It's things that I ended up doing because I wanted to do object-oriented stuff in Rust. So yeah, just a warning, you probably shouldn't be using this stuff, but if you ever find yourself in a situation where you need to do it, then hopefully I can save you some time with these things. Um, okay, so the first one actually isn't such an anti-pattern. It's something you will come across in many Rust talks where they tell you that you need to use IDs instead of references. As I just said, Rust doesn't like storing references everywhere. So for graph, for instance, what you need to do is instead of a node keeping references to its children, it just keeps a list of their IDs. And then what the graph becomes is just a hash map which maps IDs to nodes. So then whenever you need to talk to a node, what you do is you just convert the ID into a reference temporarily, essentially. And that's where the magic comes in. You just keep this reference alive for a short moment. But the long-term thing which is maintained is just references, and the borrow checker is very happy with this. Yeah, it works. It's what I ended up doing for my graph because obviously I have a scene graph, so I needed a graph where everything points to children. The one thing I just want to warn you about here, which was not really discussed in any of the talks, is that the moment you start using IDs everywhere, you kind of introduce the possibility for memory leaks again. Yeah, it's this graph right here won't do it, obviously, because this thing can't even delete nodes, or maybe that's a sign that it does delete memory. The point is, for instance, what you can do is once you create something, it's not necessarily inside the graph. It's like let's say you have some data structure where you reference stuff by IDs. Nothing prevents you from allocating a new element inside some sort of function, and then you get an ID back, and then you just drop that reference at the end of the function. That reference is gone now. You've got no way of getting that thing in. You don't know what the ID is anymore. You're never going to be able to reference that thing again. So, and Rust isn't going to realize that this has happened because of this ID to actual item mapping. And then obviously you can also have dangling references. That's the other thing that can happen. Nothing prevents you from handing out an ID and then just deleting the thing internally in the data structure. And yeah, then your ID doesn't point to anything sensible anymore or reference anything sensible anymore. It's not going to cause a hard crash. Like what it's going to do in this case is it's just going to give you an option none back. And then if you're lazy and you do an unwrap, then it's going to give you a hard crash. But yeah, so this is something which works, and many people tell you to do it. But I just want to tell you, be careful. You can, if you just go crazy, you can actually leak memory if you do this. And then the other thing I quickly want to show you is that so when I walked through my implementation for the rectangle node, you saw all these associated types. So something that I wanted to have is that you've got, say, a common base class which implements some kind of functionality, and then you can compose. So for instance, this would be the internals of the node, and it's got a function like, say, how to render it. And then you've got the superclass, which combines a lot of these individual components, and then you compose a super thing just by having a few of these lines. So I wanted to basically just build a high level component from individual components, which I guess is kind of like inheritance in Rust. I don't know. It's not really the same thing, but I don't know. It is what it is. So the problem that I ran into is that now getting here is quite easy. The problem that I had is that I wanted to keep a list of these things, right? These are my top level node handles, and I wanted to keep a list of them because I needed to well, I needed to walk through this list in order to render the nodes. And obviously, it wasn't actually a list; it was like the graph hash map thing. But whatever. The point is, I needed to keep a lot of these things in some kind of container, and you can't have a vec of box then super. It doesn't allow you to do this because super isn't. I'm not sure what the correct Rust term is, but it's basically not a fully qualified type. Okay. Whenever you talk about super, you also need to say what T is. You can't just say super. It's not a type you can put in here. And this is something that I struggled a lot with, and I had to ask for some help. But I finally found out that the way you do this type, you can do what I wanted to do, is you create a new trait called, you can call it whatever you want. I called it any super. And then what you can do is you can have Rust automatically implement any super for all the supers that you have. And the syntax is just to say, where is the super, and the associated type T is of type, implements base. And then, unfortunately, this is a bit of boilerplate. You have to actually write this line where you forward the function on your any super to the original super. It's not that bad. And then what you can do is then you can have a vector of box then any super. And this is basically just a vector of pointers. So obviously the reason why you can't actually have the reason it needs to be pointers is because all of these things have different sizes. There's no constraint that all any supers need to be the same size. It completely depends on the size of the internal struct here. So that's why you do need to have a box, which in Rust is basically just heap allocated memory, which basically is just a pointer. So this is a vec of pointers, and then this is how you keep a list of these things. And then the other trick I came to, which I talked about earlier, is the implicit sharing. If you're familiar with Qt, this is probably something that you're very familiar with. It's just the idea where what you actually create is just a handle, and you create a clonable handle, and that handle internally points to some kind of data structure. Here it's inner, and then you use RC, which is like C++ shared pointer. So internally you have a shared pointer to the shared data. This is how you allocate it. And then what happens is whenever you call something on this handle, it basically just forwards the operation to the internal data. And this is just the ref cell here is, as I spoke about earlier in Rust, I call this internal mutability. So by default, RC doesn't allow you to mutate what it owns, it points to whatever. But ref cell is something that you can. Ref cell basically allows runtime borrow checking. So on runtime, it allows you to borrow the item either mutably or immutably. And then what it will do is it will introduce a runtime crash if you break the rules of having a mutable reference and a non-mutable reference at the same time. And this is basically just for cases where it's not possible for the Rust compiler to analyze borrowing statically. Then you need to resort to refcell, so it does it on runtime. But it still ensures the same safety. You still need to, it now becomes your responsibility to make sure you're not trying to mutate something while you've got the non-mutable reference as well. But that shouldn't really happen because, because what's happening is you're only borrowing it for very short periods when you call functions like increment or print. You're only temporarily borrowing it. The rest of the time, you've just got this handle which knows how to get to the internal data. And then the interesting thing that this allows you to do is you can easily clone the handle and put it inside a boxed closure and then move this box closure anywhere, which I used it, for instance, for the callbacks. Now, I really don't know if this is a, is a good pattern or not. It works for me, especially when I tried having this object-oriented approach, but maybe there's something. If you can come up with a better solution to your specific problem, then you probably have to, because a lot of this looks wrong. Like whenever you see something like this looks awkward. This cloning, this looks very awkward. So it's not ideal, but this is how you do it if you have to. The reason I say it can panic is if you're maybe like if you're on a multi-threaded case and you're trying to increment and print at the same time, then it's going to cause a panic. This actually won't multi-thread right now because I'm using RC. To even allow you to try multi-threading, you'd need to replace it with an arc, which is an atomic RC. But once you do that, then it might actually panic if you try to call both these things at the same time on different threads. And yeah, I mean, it might just be dodgy. I don't know. It's up to you to decide, but here is it. So then lastly, I'd like to give a few tools and resources if this is something that you want to start playing with on your own. The first one is really just a link to the Rust book. So if you've never worked with Rust before, I really recommend you read the book first. Because Rust isn't a language you can just jump into and start programming. It's going to end in tears. You really need to understand things like the borrow checker before you get into it. You just have to. And then the second link here is a very nice tutorial on WebGPU in Rust. So this is how I learned WebGPU. I basically just followed this tutorial, implemented everything there, and then just started building my prototype on top of the patterns they showed here and the example code. Then for an IDE, as you saw, I'm using CLion at the moment. You can also use VS Code, but for me, it didn't work out that great. The language server sort of just crashed the whole time. Appears to be something wrong with that, whereas the CLion Rust plugin works really well. I'm quite impressed with that. It works. So if you want something which is a bit more robust at the moment and fun to work with, then I'd recommend going for the CLion one. But it's not important what you use. And then the other link I've got here is for the Qt documentation on the scene graph in Qt. So if you want more information on how the Qt scene graph works, as I said, it's for if you want to try and do what I did, maybe a bit better, hopefully a bit better, then maybe just go read up on how Qt does this type of thing. And yeah, then the very last thing I want to get to is just a short discussion on, what's next. So I think the absolute main shortcoming of what I have right now is just the API. As I alluded to earlier, it's a really ugly, really imperative API. We need to come up with something nice. Specifically, I'd like something like the modern frameworks like React.js or Flutter or things like that, which are responsive. So you've basically got these special variables, which are called state variables. And then whenever you update that state variable, everything just happens. Every node that referenced that state variable should know how to update itself in response to that variable being updated. You don't need to manually go call set this on every individual node which is affected. And I do want that to be efficient, right? In Flutter, it's actually not that efficient right now. As far as I am aware, in Flutter, how it works is, each individual widget can have a bunch of state variables, and then what happens is when you update any state variable on the widget, it basically calls render, or I can't remember what they call it, but in React world that would be the render function, and then they re-render the same. They re-render the entire widget in response to the state change, and React.js works like this as well. In the web world, they've now got this thing called Svelte, which tries to not do that. It tries to only update what needs to be updated in response to the specific state variable change. It doesn't call re-render on the entire component. QML basically works like this as well. QML doesn't really have special state variables as such. It's got the concept of properties, which are basically the same thing, but in QML almost everything is a property anyway. So that's why I don't want to call it a special thing, because almost everything is a property. And in QML, whenever you change a property, then everything bound to it automatically gets reevaluated. So yeah, I what I specifically want is something along these lines in Rust, but I do still need to figure out, how do you firstly do this in Rust? How do you make it look right in Rust? How do you make it perform right, etc., etc. Then, what would also be nice is to have more complex things on top of these. So to not just have individual state variables, but to be able to, for instance, say x plus 10, and then have that whole expression reevaluate whenever x changes, instead of being able to bind just to x. That would be a very nice thing to add, if possible. I'm not sure if all libraries currently have this. Like in React, for instance, you kind of need to build that yourself. You need to create a new state variable and update that. But it's not really a problem in React, because, as I said, the whole render function of the widget is called when any state changes. So if you've got an expression x plus 10, that is implicitly going to be reevaluated, because the whole render function is reevaluated. But I don't want that whole render function thing. Um, I want individual state variables to map through directly into the node and only update what needs to be updated when the state is changed. So that's kind of what I want to go after, and I want to be also then say that I want, for instance, x plus 10 to be bound directly into the right property on the node. Yeah. And then for any re-implementation of this, I'd strongly try to take a non-object oriented approach from the beginning this time, because I ended up having to rework a lot of stuff to force it to work on Rust, because I had a very object-oriented mindset from the beginning. Something that I am looking at right now is ECS-based approach. So ECS stands for Entity Component System, which is a paradigm very commonly used for game engines, which fits very nicely with the Rust borrow checker, because it's also based on this concept of, you don't use references, you use IDs, and you split your whole rendering logic into these individual stages. And that gives you incredibly high performance for game engines, and Rust actually already has plenty of game engines. As far as I know, all of them are built around this ECS principle. So I haven't quite figured out how I want to build, or if I necessarily want to do that, but I am playing in my head still at the moment with the idea of building the whole rendering pipeline around an ECS. So the idea that I have right now is to take that thing I ended up with for event handling, where you've got the caller map. I want to take that a lot further, right? So I want to take all these nodes that I have right now. As you remember, the node had all those individual components, and each of them were, had its own ref cell. So what I'm thinking about is maybe, breaking up the nodes and having all of those individual data structures inside the ECS, and then having a very pipelined approach where, for instance, the first pipeline stage looks at all the state that has changed since the previous render call, and then it sets, it creates a list of, with dirty flags, it creates a list of internal node properties which need to be updated. Then it goes through that list, mutates all the properties, and while doing that, it also builds a new list of I'm not sure what to call it, of things which need to be sent to the GPU, basically. So as I said, you'd have one stage which reevaluates all the bindings, and then the next stage looks at, okay, which bindings have actually changed. So what do we now need to send to the WebGPU instruction queue? And that would be the next pipeline stage. And then after you've updated the WebGPU instruction queue, then you'd go into the final stage where you actually call render. And then, of course, you'd have other stages where you process user input, generate events, etc., etc. So the idea that I'm looking at here is really splitting up all the things you can do into different stages and keeping the data separate. Maybe with an ECS library, maybe just taking inspiration and building a custom library. I don't know yet. And then, yeah, of course, the most important part of what to do next is just make sure that it's awesome. I think that's pretty obvious. Thanks for listening.
So hello again, and we are here at the end of a very interesting talk. We would like to welcome Gerhard back with us again so that we can start the Q&A session. The Q&A chat will be open in a minute, and you can ask your questions over there. We hope that you have enjoyed this talk. It was very long and detailed and very informative, of course. Welcome back there.
Oh, thanks.
Okay. So let's see if we can get some questions. In the meantime, I would like to remind you about our future talks. You can subscribe to our newsletter, as you can see. Okay, so let's see. We have the first question. Have you done any testing or measurements on whether the Qt architecture is truly more efficient on a GPU than the Flutter architecture?
No, so I haven't actually tested this yet. It's pretty complicated to test really just on an architecture level because there are so many other implementation details that you need to take into account. So it's really hard to have a fair comparison on just the architecture level. So right now I'm basing it more just on intuition that a more GPU-centric design should perform better. But I think we at KDAB are looking at this. So at some point we will do a more thorough evaluation of exactly what the performance differences are between at least Qt and Flutter as they are implemented.
Thank you very much. And let's see if we can get any other questions. We still have our newsletter button on the top of the page that you can click to see our events. Okay, so have you seen 60 FPS? It's a take on QML from one of the original authors of QML. What do you think about it if you have seen it?
Yes, I have actually seen it. It is quite interesting. It's not 100% focused on Rust as this is because it's got, they try to target both Rust, C++, and JavaScript, if I remember correctly, with their own language, which I think they call .60, which is similar to QML. The main reason I haven't looked into it much yet is actually just around licensing, because at the moment it's licensed under GPL and then with a commercial license. So it doesn't look like the type of thing that would really, it's not going to get the general Rust community behind it with that kind of license. And that kind of license is creating a lot of issues with Qt itself right now. So yeah, as I said, the main thing which prevented me from really looking in detail into it is simply the license. But I did look into it a bit, and it's backed by you can choose two backends at the moment. The one is a Q Painter, and the other one I can't remember right from the top of my head. But so basically, that also implies that deep down in the pipeline, it also does imperative drawing, kind of like Flutter. So even though it does have QML at the top level, I think it's very different from Qt Quick at the bottom level. So basically, it's not exactly the same thing at the bottom, but what they are aiming for is, at least on the developer experience level, it is very similar to QML. But yeah, it does look very interesting. I'm just not sure if they're ever going to get it really big with the license they have right now, unless they get some funding to develop it themselves. But it's definitely something to watch out for.
Thank you. Let's see. We should have. Okay, we have another question from Nathan. You mentioned React.js. The more modern React uses hook methods to inject mutability into otherwise function, with the return value from the render function being immutable. That I'm really sorry, this is a little convoluted.
Yeah, I'm trying to read it myself.
Okay.
Yeah, so the question is, you mentioned React.js, or more modern React uses hook methods to inject mutability into otherwise functions, with the return value from the render function being immutable. That then passes through a reconciliation pass to convert to render level primitives. Maybe in your framework, it could be the GPU draw list. Would this help your framework move away from the object ref problem? Yes, I think doing something along the line of React with hooks is definitely something to consider. Yeah, I haven't looked into it that much. As I said, I've been working mostly on the back end part right now. I haven't played too much with what's the top level yet. But doing it like React with hooks, if I recall correctly, the Moxie library that I referenced to, that is very inspired by React, and it uses tracing of when you call functions to do something very similar to React hooks. So basically, it traces every function that you call, and then maintains a tree of that, and then it sort of like diffs that to the previous tree. So yeah, I think this is definitely a direction to look in. But yeah, I haven't gone that far yet. But yeah, I think Moxie, for instance, does something similar to this.
Thank you, Gerhard. In the meantime, I can remind you that you can find the next event also on the website, rustlab.it, other than in our newsletter. And you can see also all our events on our YouTube channel, or the past events, and also this one starting tomorrow, I think, on our YouTube channel. So we have a question from Davide, and the question is, implicit sharing could be done using RWLock. Did you go with RefCell for performance reasons?
Yeah, so I guess you could argue that RWLock is essentially just the multi-threaded version of RefCell. I mean, don't quote me on that, but that is my understanding of it. And right now, I don't have any multi-threading in my application yet. So using RWLock would be slower, because then I need to do, locking and atomic operations every time. Whereas I don't need that yet. But it is sort of, I'm not sure if you really want if you really can make this thing multi-threaded in the first place, because the timing of everything sort of becomes a bit of an issue as well. Yeah, I haven't looked at it yet, but there are plenty of places where things can go wrong, and most GUI frameworks right now are pretty single-threaded. So, it just keeps the logic simpler. So I'm not sure. I think WebGPU, or I'm pretty sure WebGPU itself is multi-threaded. Like OpenGL, for instance, was quite tricky to do multi-threaded things with. So in theory, this thing could be made multi-threaded, but it does add a lot of complexity in a lot of places. So that's why I've started with single-threaded and RefCell. Yeah, like I think multi-threading would be added later, and yeah, I'm not entirely sure you can. It's that easy to build a safe pipeline where everything is multi-threaded, because, for instance, somewhere inside the web GPU render loop, for instance, I had a lot of issues with ownership. I can't quite recall the function, but that thing, for instance, just you wouldn't be able to multi-thread that at all. So yeah, I guess this is not a very good answer to your question, but yeah, right now I'm using RefCell just because it's a single-threaded thing at the moment.
Okay, so David is thanking you, and thank you, David, for the very interesting question. And let's wait another few minutes to see a little bit if there is anybody who wants to ask another question. Otherwise, I can point you to our Discord channel where the conversation can continue on this subject. And I would like to remind you once again to subscribe to our newsletter and to follow our YouTube channel. So we thank Gerhard for an extremely interesting talk and for engaging with our audience with the Q&A session. And I will welcome you to the next event of RustLab. Thank you very much and good evening.
Oh, thanks.